Good day, guys. Our topic for today is all about linear programming applications in marketing, finance, and operations management. Linear programming has proven to be one of the most successful quantitative approaches to decision making. In this chapter, we present a variety of applications such as marketing, finance, and operation management. Under marketing applications, there is media selection and marketing research. Under financial applications, there is portfolio selection and financial planning. Under operations management, there is a make or buy decision, production scheduling, workforce assignment, and binding problems. Marketing applications under media selection. One of the application of linear programming in marketing is media selection. It can be used to help marketing managers to allocate fixed budget to various advertising media. The objective is to maximize reach, frequency, and quality of exposure. Restrictions on the allowable allocation usually arise during consideration of company policy, contract requirements, and media availability. Example: Relax and Enjoy Lake Development Corporation is developing a lakeside community at a privately owned lake. The primary market for the lakeside lots and homes includes all middle and upper income families within approximately 100 miles of the development. Relax and Enjoy employed the advertising firm of Bone, Phillips and Jackson, in short BP&J, to design the promotional campaign. After considering possible advertising media and the market to be covered, BP&J recommended that the first month advertising be restricted to 5 media. At the end of the month, BP&J will then reevaluate its strategy based on the month's result. BP&J collected data on the number of potential customers reached, the cost per advertisement, the maximum number of times each medium is available, and the exposure quality rating for each of the 5 media. The quality rating is measured in terms of an exposure quality unit, a measure of the relative value of one advertisement in each of the media. This measure, based on BP&J's experience in the advertising business, takes into account factors such as audience demographic, age, income, and education of the audience reached. Relax and Enjoy provided BP&J with an advertising budget of $30,000 for the first month's campaign. In addition, Relax and Enjoy imposed the following restrictions on how BP&J may allocate these funds. At least 10 television commercials must be used, at least 50 potential customers must be reached, and no more than $18,000 may be spent on television advertisements. So, what advertising media selection plan should be recommended? So, mauna siya ang 5 ka advertising media, which is TV, newspaper, and radio. So, in TV, kadua siya gamiton, which is daytime TV, which is ang number of potential customers reach 1,000. Yung cost per advertisement is 1,500. Maximum times available per month is 15, and exposure quality units of 65. In evening TV naman, the potential customers reached is 2,000. Cost per advertisement is 3,000, maximum times available per month is 10, and exposure quality units is 90. Daily newspaper, yung number of potential customer reach is 15, cost per advertisement is 400, available niya per month is 25, and exposure quality units is 40. Sunday newspaper magazine, yung number of potential customer reach is 2,500, cost per advertisement is 1,000, maximum times available per month is 4, and exposure quality units of 60. And the radio naman, Number of potential customer reach is 300. Cost per advertisement is 100. Maximum times available per month is 30. Exposure quality units of 20. The decision to be made is how many times to use each medium. We begin by defining the decision variables. DTV stands for daytime TV used, ETV evening TV used, DN is daily newspaper used, SN is Sunday newspaper used, and R for radio. So, the data on quality of exposure that shows that each daytime TV advertisement is rated at 65 exposure quality units. Thus, an advertising plan with daytime TV advertisement will provide a total of 65 exposure quality units. Muna siyang 65 sa iyang ato ang objective function 65 DTV, and continuing with the data evening TV rated at 60 exposure quality units, daily newspaper is 40 exposure quality units, and Sunday newspaper is 60 exposure quality units, and radio is 20 exposure quality units. So with the objective of maximizing the total exposure quality units for the overall media selection plan, the objective function becomes maximize 65 DTV plus 90 ETV plus 40 DN plus 60 Sunday newspaper plus 20 radio. Muna siya ang exposure quality. So we now formulate the constraint for the model from the information given. So muna na siya guys. Makita niyo dito sa table. Under availability of media, mauna siya ang DTV not less than equal to 15. ETV is not less than equal to 10. DN is not less than equal to 25. Sunday newspaper magazine is not less than 4 and not less than equal to 4, and R is not less than equal to 30. So under budget, makita sa atin yun sa budget, 50, 15 DTV, 3000 ETV, 400 DN plus 100 SN plus 100 R is not less than equal to 30. Kaya maura man 30,000 I mean. Kaya maura man na ang hatag nga budget sa Relax and Enjoy sa BPNJ for the first month campaign. So under TV television, DTV restrictions, DTV and ETV is not greater than equal to 10. And 1,500 DTV plus 3,000 ETV is not less than equal to 18,000. Yeah. Under sa customer reach, 1,000 DTV plus 2,000 ETV plus 1,500 DN plus 2,500 SN plus 300 R is greater than equal to 50,000 mo na siya. So the Relax and Enjoy should consider reducing the requirement of having at least 10 television commercials. As possible shortcoming of this model is that even if the exposure quality measure were not subject to error, it offers no guarantee that maximization of total exposure quality will lead to maximization of profit or of sales. However, this issue is not a shortcoming of linear programming, rather, it is a shortcoming of the use of exposure quality as a criterion. If we could directly measure the effect of an advertisement on profit, we could use total profit as the objective to maximize. Marketing application under marketing research. A firm conducts marketing research to learn about consumer characteristics, attitudes, and preferences. Marketing research services include designing the study, conducting surveys, and analyzing data collected and providing recommendations for the client. In the research design phase, targets or quotas may be established for the number of types of respondents to be surveyed. The marketing research firm's objective is to conduct the survey so as to meet the client's needs as at a minimum cost. Example, market survey specializes in evaluating consumer reactions to new products, services, and advertising campaign. A client firm requested MSI's assistance in ascertaining consumer reactions to a recently marketed household product. During meetings with the client, MSI agreed to conduct door-to-door personal interviews to obtain responses from households with children and households without children. In addition, MSI agreed to conduct both day and evening interviews. The client contract called for MSI to conduct 1,000 interviews under the following quota guidelines. First, quota guidelines is interview at least 400 households with children, interview at least 400 households without children, and the total number of households interviewed during the evening must be at least as great as the number of households interviewed during the day. At least 40% of the interviews for households with children must be conducted during the evening, and at least 60% of interview for households without children must be conducted during evening. So because of the interviews for household with children take additional interviewer time, and because evening interviewers are paid more than daytime interviewers, the cost varies with the type of interview. So here is the estimate of the interview cost as. So, mao na siya ang cost under household with children. Ang iyang day is 20, ang iyang evening is 25. Ang iyang cost household with no children is iyang day is 18, ang iyang evening is 20. So, in formulating the linear programming model for the MSI problem, we utilize the following decision variables notation. DC stands for daytime interviews of household with children. EC is evening interviews of household with children. DNC, the number of daytime interviews of household without children. And ENC is the number of evening interviews of household without children. So, mao niya itong objective function. 20 DC plus 25 EC plus 18 DNC plus 20 ENC. The constraint is mao ni DC plus EC plus DNC plus ENC is equal to 1,000. Niya mo ni ang iyang mga specification. Household with children, household without children, at least many evening interviews as they interviews muna EC plus ENC is greater than equal to DC plus DNC, and at least 40% of interviews of household with children during the evening, and at least 60% of interview of household without children during the evening. So, mao na siya ang katong iyahang kuan guys, kanang quota guidelines. So, mao na ni siya. Same man gyapon nito sa ibabaw. Constraint 6 shows that requiring one or more household without children to be interviewed during the evening will increase cost of 2. That's all. Thank you.
Linear programming can be applied in problem situation involving capital budgeting, asset allocation, portfolio selection, financial planning, and many others. In this section, we describe a portfolio selection problem and a problem involving funding of an early retirement program. For the portfolio selection, Problem involves situation in which a financial manager must select specific investment, for example, stocks and bonds, from a variety of investments alternatives. Manager of mutual funds, credit unions, insurance companies, and banks frequently encounter this type of problem. The objective function for portfolio selection problems usually is maximization of expected return or minimization of risk. The constraints usually take the form of restrictions on the type of permissible investment, company policies, maximum permissible risk, and so on. Problems of this type have been formulated and solved using a variety of mathematical program techniques. In this section, we formulate and solve a portfolio selection problem as a linear problem. So for the portfolio selection example, Wealthy Mutual Funds Incorporated, located in New York City, Wealthy just obtained $100,000 by converting industrial bonds to cash and is now looking for other investment opportunities for these funds. Based on Wealthy's current investments, the firm's top financial analyst recommends that all new investments be made in the oil industry, steel industry, or in government bonds. Specifically, the analyst identified 5 investment opportunities and project their annual rates of return. Management of Wealthy imposed the following investment guidelines. Number 1. Neither industry, oil or steel, should receive more than $50,000. Number 2. Government bonds should be at least 25% of the steel industry investments. Number 3. The investment in Pacific Oil, the high return but higher risk investment, cannot be more than 60% of the total oil industry investment. So, what portfolio recommendation investments and amounts should be made for the available $100,000? Give the objective of maximizing project return subject to the budgetary and managerially imposed constraints. We can answer this question by formulating and solving a linear programming model of the problem. The solution will provide investment recommendations for the management of wealthy mutual funds. So, for the portfolio example, investment opportunities of mutual funds under investment is Atlantic Oil, which has projected rate of return 7.3%, Pacific Oil 10.3%, Midwest Steel has 6.4%, Hoover Steel has 7.5%, Government Bonds has 4.5%. So let A represent dollars invested in Atlantic Oil, P represent dollars invested in Pacific Oil, M represented dollars investment in Midwest Steel, H is represented dollars invested in Hoover Steel, G represented the dollars invested on government bonds. Using the project rates of return shown in Table 3, we write the objective function for maximizing the total return for the portfolio as max 0.073A plus 0.103P plus 0.064M plus 0.075H plus 0.045G. The constraints specifying investment of the available $100,000 is A plus P plus M plus H plus G is equals to 100,000 available funds. The requirements that neither the oil nor the steel industry should receive more than $50,000 are A plus P is less than or equal to 50,000, M plus H is less than or equal to 50,000, then the requirements that government bonds be at least 25% of the steel industry investment is expressed as G is greater than or equal to 0.25 M plus H. Finally, the constraints that Pacific Oil cannot be more than 60% of the total industry investment is P is less than or equal to 0.60 A plus P. By adding the non-negativity restrictions, we obtain the complete linear programming model for the wealthy mutual funds investment problem. Solution to this linear program is shown in figure 4.3. The table 4.4 Kinesia shows how the funds are divided among the securities. Note that the optimal solution indicates that the portfolio should be diversified among all the investment opportunities except Midwest Steel. The project annual return for this portfolio is $8,000, which is an overall return of 8%. The optimal solution shows the dual value for constraint 3 is 0. The reason is that the steel industry maximum isn't binding constraint. Increase in the steel industry limit of $50,000 will not improve the value of the optimal solution. Indeed, the slack variable for this constraint shows that the current steel industry investment is $10,000 below and its limit of $50,000. The dual values for the other constraints are non-zero, indicating that these constraints are binding. So the dual value of 0.069 for constraint 1 shows that the value of the optimal solution can be increased by 0.069 if $1 more can be made available for the portfolio investment. If more funds can be obtained at a cost of less than 6.9%, management should consider obtaining them. However, if a return in excess of 6.9% can be obtained by investing funds elsewhere other than in these 5 securities, management should question the wisdom of investing the entire $100,000 in this portfolio. Similar interpretation can be given to the other dual values. Note that the dual value for constraint 4 is negative at negative 0.024. This result indicates the increasing the value on the other hand. On the other hand side of the constraint by 1 unit can be expected to decrease the objective function value of the optimal solution by 0.024 in terms of the optimal portfolio. Then, if wealthy invest $1 more in government bonds beyond the minimum requirement, the total return will decrease by $0.024. To see why this decrease occurs, note again that the dual value for constraint 1, that the marginal return of the funds invested in the portfolio is 6.9%, the average return is 8%. The rate of return on government bonds is 4.5%. Thus, the cost of investing $1 more in government bonds is the difference between the marginal return on the portfolio and the marginal return on government bonds, 6.9% minus 4.5% is equals to 2.4%. The optimal solution shows that Midwest Steel should not be included in the portfolio. M equals 0. The associate reduced cost for M of negative 0.011 tells us that the objective function coefficient for Midwest Steel would have to increase by 0.011 before considering the Midwest Steel investment alternative would be advisable. With such an increase, the Midwest Steel return would be 0.064 plus 0.011 is equals to 0.075, making this investment just as desirable as the current use Hoover Steel investment alternative. Finally, a simple modification of the wealthy linear programming model permits determining the fraction of variable funds invested in each security. That is, we divide each of the right-hand side values by 100,000, then the optimal values for the variables will give the fraction of funds that should be invested in each security for a portfolio of any size. Next one is financial planning. Linear programming has been used for a variety of financial planning applications. The management assigns in action. General Electric uses linear programming for solar energy investment decisions. Describe how linear programming is used to evaluate various scenarios to guide capital investment strategy over a long-term horizon. So, financial planning example. Letter Corporation established an early retirement program as part of its corporate restructuring. At the close of the voluntary sign-up period, 68 employees had elected early retirement. As a result of these early retirements, the company incurs the following obligation over the next 8 years. So the cash requirements in thousands of dollars are due at the beginning of each year, meet the 8 yearly financial obligation as they come due. The financing plan for the retirement program includes the investment in government bonds as well as savings. The investment in government bonds are limited to 3 choices. The government bonds have a par value of $1,000, which means that even with different prices, each bond pays $1,000 at maturity. The rates shown are based on the par value. For purpose of planning, the treasurer assumes that any funds not invested in bonds will be placed in savings and earn interest at an annual rate of 4%. So we define the decision variables as follows. F. Total dollars required to meet the retirement plan's 8-year obligation. B1. Unit of Band 1 purchased at the beginning of year 1. B2. Units of Band 2 purchased at the beginning of year 1. B3. Units of Band 3 purchased at the beginning of year 1. SI. Amount placed in savings at the beginning of year I for I equals to 1 up to 8. The objective function is to minimize the total dollars needed to meet the retirement plan 8-year obligation, or MINF. A key feature of this type of financial planning problem is a constraint must be formulated for each year of the planning horizon. In general, each constraint takes the form funds available at the beginning of the year minus funds invested in bonds and placed in savings is equals to cash obligation for the current year. The funds available at the beginning of year 1 are given by F with a current price of $1,150 for Band 1, an investment expressed in thousands of dollars. The total investment for B1 units of Band 1 would be 1.5 B1. Similarly, the total investment in B2 and 3 would be 1B2 and 1.35B3 respectively. The investment in savings for year 1 as SI using this result and the first year obligation of 430, we obtain the constraint for year 1 F minus 1.15B1 minus 1B2 minus 1.35B3 minus S1 is equals to 430 in just year 1. Investment in bonds can take place only in this first year and the bonds will be held until maturity. The funds available at the beginning of year 2 included the investment returns of 8.875% of the par value of 5.5% on the par value of band 2, 11.75% on the par value of band 3, and 4% on savings. The new amount to be invested in savings for year 2 is S2 with an obligation of 210. The constraint for year 2 is 0.08875 B1 plus 0.055 B2 plus 0.1175 B3 plus 1.04 S1 minus S2 is equals to 210 in just year 2. Similarly, the constraints for year 3 to 8 are 0.08875 B1 plus 0.055 B2 plus 0.1175 B3 and plus 1.04 S2 minus S3 is equals to 222 year 3. In year 4, 0.08875 plus B1 plus 0.055 B2 plus 0.1175 B3 plus 1.04 S3 minus S4 is equal to 231 in year 4. 0.08875 B1 plus 0.055 B2 plus 0.1175 B3 plus 1.04 S4 minus S5 is equal to 240 in year 5. 1.08875 B1 plus 0.055 B2 plus 0.1175 B3 plus 1.04 S5 minus S6 equals to 195 year 6. 1.055 B2 plus 0.1175 B3 plus 1.04 S6 minus S7 is equals to 225 in year 7. 1.1175 plus B3 plus 1.04 S7 minus S8 is equals to 255 year 8. Note that the constraint for year 6 shows that the funds available from the band 1 are 1.08875 B1. The coefficient of 1.08875 reflects the fact that band 1 matures at the end of year 5. As a result, the par value plus the interest from band 1 during the year 5 is available at the beginning of year 6. Also because band 1 matured in year 5 and become available for use at the beginning of year 6, the variable B1 does not appear in the constraints for year 7 and 8. Note the similar interpretation for band 2, which matures the end of the year 6 and has the par value plus interest available at the beginning of year 7. In addition, Bond 3 mature at the end of year 7 has the par value plus interest available at the beginning of year 8. Finally, note that a variable S8 appears in the constraint of year 8. The retirement fund obligation will be completed at the beginning of year 8, so we anticipate that S8 will be 0 and no funds will be put into savings. However, the formulation includes S8 in the event that the bond income plus interest from the savings in year 7 exceed the 255 cash requirement for year 8. Thus, S8 is a surplus variable that shows any funds remaining after the 8-year cash requirements have been satisfied. The optimal solution to these 12 variables, 8 constraints linear program is shown in figure 4.4 with an objective function value of 1,728.79385. The total investment required to meet the retirement plan 8-year obligation is $1,728,794 using the current prices of $1,150, $1,000, and $1,350 for each of the bands respectively. We can summarize the initial investment in the 3 brands as follows. The solution also shows that $636,148 will be placed in savings at the beginning of the first year by starting with $1,728,794. The company can make the specified bond and savings investment and have enough left over to meet the retirement program's first year cash requirement of $430,000. The optimal solution in figure 4.44 shows that the decision variables S1, S2, S3, and S4 are all greater than 0, indicating investment in savings are required in each of the first 4 years. However, interest from the bonds plus the bond maturity incomes will be sufficient to cover the retirement program's cash requirements in year 5 to 8. The dual value have an interesting interpretation in this application. Each right-hand side value corresponds to the payment that must be made in that year. Note that the dual values are positive, indicating the increasing the required payment in any year by $1,000 would increase the total funds required for the retirement program's obligation by $1,000 times the dual value. Also note that the dual value shows that increase in required payments in the early years have the largest impact. This makes sense in that there is little time to build up investment income in the early years versus the subsequent years. This suggests that if you let phases increases in required payments, it would benefit by deferring those increases to later years if possible.
Good day, everyone. This is Nelmida, and I am the last reporter for Chapter 4, and I am going to discuss about Operation Management Application. Good day, everyone. This is Nelmida, and I am the last reporter. Linear programming application developed for production and operation management include scheduling, staffing, inventory control, and capacity planning. In this section, we describe examples with make or buy decision, production scheduling, and workforce assignments. We will illustrate the use of linear programming model to determine how much of each several components parts of a company should manufacture and how much it should purchase from an outside supplier. A make or buy decision example. The Hunter's company markets various business and engineering products. Currently, Hunter is preparing to introduce two new calculators, one for the business market called the financial manager and one for the engineering market called the technician. Each calculator has three components, a base, an electronic cartridge, and a faceplate or top. The same base is used for both calculators, but the cartridges and tops are different. All components can be manufactured by the company or purchased from outside suppliers. Hunter's company has two new calculators, the financial manager and the other one is called technician. When we say financial managers are responsible for the financial reports, direct investment activities, and develop strategies and plans for the long-term financial goods of their organization. And the technician is a worker in a field of technology who is proficient in the relevant skill and technique with a relatively practical understanding of the theoretical principles. And the three components of calculator are base, electronic cartridge, faceplate or top. Table 4.5 Manufacturing costs and purchase prices for Hunter's calculator components. Company forecasters indicate that 3,000 financial manager calculators and 2,000 technician calculators will be needed. However, manufacturing capacity is limited. The company has 200 hours of regular manufacturing time and 50 hours of overtime that can be scheduled for the calculators. Overtime involves a premium at the addition cost of $9 per hour. The problem for handlers is to determine how many units of each component to manufacture and how many units of each component to purchase. First, we will define the decision variables as follows. BM is equals for number of bases manufactured. BP is equals to number of bases purchased. FCM is equals to number of financial cartridges manufactured. FCP is equals to number of financial cartridges purchased. TCM is equals to number of technician cartridges manufactured. TCP is equals to number of technician cartridges purchased. FTM is equals to number of financial tops manufactured. FTP is equals to number of financial tops purchased. TTM is equals to number of technician tops manufactured. TTP is equals to the number of technician tops purchased. OT is equals to number of hours of overtime to be scheduled. The objective function. Minimize of 0.5 bm plus 0.6 bp plus 3.75 fcm plus 4 fcp plus 3.3 tcm plus 3.9 tcp plus 0.6 ftm plus 0.65 ftp plus 0.75 ttm plus 0.78 ttp plus 9 OT. The objective function is to minimize the total cost, including manufacturing costs, purchase costs, and overtime costs using the cost per unit data in Table 4.5 and under over the premium cost rate of $9 per hour. The 5 demands constraints. BM plus BP equals 5,000 bases. FCM plus FCP equals 3000 financial cartridges, TCM plus TCP equals 2000 technician cartridges, FTM plus FTP is equals to 3000 financial tops, and TTM plus TTP equals 2000 technician tops. These are the 5 demands of constraints. The first 5 demands of constraints specify the number of its components needed to satisfy demand for 3000 financial manager calculators and 2000 technician calculators, a total of 5000. Base components are needed with a number of other components depending the demand for the particular calculator. So, two constraints are needed to guarantee that the manufacturing capacity for regular time and overtime cannot be exceeded. The first constraint limits overtime capacity to 50 hours or overtime less than or equals to 50. The second constraint states that the total manufacturing time required for all components must be less than or equal to the manufacturing capacity, including regular time, plus state that the total manufacturing capacity constrained in minutes with a 200 hours of regular time capacity becoming 60 times 200 equals 12,000 minutes. The actual overtime square required is unknown at this point, so we will write the overtime as 60 over the time minute using the manufacturing times from the table 4.6. So this is the solution for Hunter's make or buy problem. The optimal solution to these 11 variables and 7 constrained linear program is shown in figure 4.5. The optimal solution indicates that all 5000 bases, financial manager cartridges, and 2000 technician cartridges should be manufactured. The remaining 2333 financial manager cartridges. Operation Management Application. Production Scheduling. This is the most important applications of linear programming, deals with multi-period planning such as production scheduling. The solution to a production scheduling problem enables the manager to establish an efficient low-cost production schedule for one or more products over several times or months. Production scheduling example. Bollinger's Electronics Company, which produces two different electronic components for a major airplane engine manufacturer. The airplane engine manufacturer notifies the Bollinger sales office each quarter of each monthly requirements for components for each of the next 3 months. The monthly requirements for the components may vary considerably depending on the type of engine the airplane engine manufacturer is producing. In arriving at the desired schedule, the production manager will want to identify the following: total cost, inventory holding cost, change in production level cost. This is the table for 3-month demand schedule for Pulling an Electronic Company. To develop the model, we let X increase month denote the production volume in units for product increase in month. Here, increase 1, 2, 2, and month 1 to 3 increase equals 1 refers to component 3, 2, 2, A increase 2 refers to component 802B, months is equal to 1 refers to April and months is equal to 2 refers to May, and month is equals to 3 refers to if component 322A costs $20 per unit produced and component 802B costs $10 per unit produced, the total production cost part of the objective function. Because the production cost per unit is the same each month, so we don't need to include the production cost in objective function that is regardless of the production schedule selected. The total production cost will remain the same. In other words, production costs are not relevant costs for the production scheduling decision under consideration. Inventory holding cost portion of the objectives function. Third portion of the objective function. A, a common assumption made in using the linear programming approach to production scheduling is the monthly ending inventories are acceptable approximation to the inventory average inventory levels throughout the month. After estimating effects of employee layoff, turnover, reassignment, training costs, and the other costs associated with fluctuating production levels, Bollinger estimates that the cost associated with increasing the production level for any month is 0.5 per unit increase. A similar cost associated with decreasing the production level for any month is $0.2 unit. Thus, we write the third portion objective function as note that the cost associated with changes in production level is a function of a change in the total number units produced in a month compared to the total number of units produced in the other production schedule application. Production level might be measured in terms of machine hours or labor hours required rather than in terms of number units per produce. Combining all three costs, the complete objective function becomes, as we know, consider the constraints. First, we must guarantee that this schedule meets customers' demands because the unit shipped can come from the current month production or from inventory card from the previous months. The demand requirement takes the fourth. Suppose that the inventories at the beginning of the 3 months scheduling period were 500 units for component 322A and 200 units for component 802B. The demand for both products in the first month, April, was 1,000 units. So, the constraints for meeting demand in the first month become 500 plus x sub 11 minus s sub 11 equals 1,000, and 200 plus x sub 21 minus s sub 21 equals 1,000. Moving the constraints to the right-hand side, so we have x sub 11 minus s sub 11 equals 500, and x sub 21 minus s sub 21 equals 800. Similarly, we need demand constraint for both products in the second and third months. We write them as follows. For month 2, S11 plus X12 minus S12 equals 3,000. S21 plus X22 minus S22 equals 500. For month 3, we have S12 plus X13 minus S13 equals 5,000, and S sub 22 plus X23 minus S23 equals 3,000. If the company specify a minimum inventory level at the end of the 3-month period of at least 400 units of component 322A and at least 200 units of component 802B, we can add the constraints S sub 13 greater than or equal to 400 and S sub 23 greater than or equal to 200. Suppose that we have the additional information on machine labor and storage capacity. One final set of constraints must be added to guarantee that increased month and the decreased month will reflect the increase or decrease in the total production of level per month. Suppose that the production level for March and the month before the start of current production scheduling before had been 1,500 units components of 322A and 1,000 units for components 802B. We have here the table 4.8 machine labor and storage capacities for Bollingers Electronics and table 4.9 machine labor and storage requirements for components 322A and 802B. Total production level of 1,500 plus 1,000 equals 2,500 units. We can find the amount of the change in productions for equipment from the relationship every introduction to March equals change using the production variables x sub 11 and variables x sub 21 in the March production of 2,500 units we have. Note that the change can be positive or negative. A positive change reflects an increase in the total production level and the negative change reflects a decrease in the total production level. We can use the increase in production for April and then decrease in production for April D1 to specify the constraint for change in total production for the month of April. And of course, we cannot have an increase or decrease in production during the same 1-month period. Thus, either one or increase or decrease of 0. If ever requires 3,000 units production, increase equals 500 and decrease equals 0. If ever requires 200 units production, increase equals 0. This approach of denoting the change in production level as the difference between non-two negative variables increase and decrease permits positive and negative changes in the total production level. If a single variable had been used to represent the change in production level, only positive change would be possible because of the non-negative requirements. Using the same approach in May and June, always subtracting the previous month's total production from the current month total production, we obtain a constraint for the second and third months of production scheduling. The initially rather small two-product remain scheduling problem has now developed in 18 variables, 20 constrained linear programming. Note that this problem we were concerned only with one type of machine, process, one type, label, and one type storage area. Actual production scheduling probably usually involves several separate linear programming programs. For instance, a problem involving 100 products over a 12 months per year could have more than 1,000 variables and constraints. From the figure 4.6, The optimal solution to the Bollinger Electronic Production Scheduling Problem Table 4.10 contains a portion of the managerial report based on the optimal solution. Consider the monthly variation in the production and inventory schedule shown in the table 4.10. Recall the event inventory cost for the component 802B is one-half the inventory cost for component 322A. Therefore, as might be expected, component 80 will produce heavily in the first month, April, and then held in inventory for a demand that will occur in the future months. Component 322A that tends to be produced with net and only small and out are carried in inventory. This is the solution of Bollinger Electronics problem. The cost of increasing and decreasing in the total production volume tend to smooth the monthly variation. In fact, the minimum cost schedule calls for a 500 unit increase in the total production in April and 2,200 unit increase in the total production in May. The May production level of 5,200 units is maintained during June. Operation Management Applications Workforce Assignment Workforce assignment problems frequently occur when production manager must make decisions involving staffing requirements for a given planning period. It also often has some flexibility, and at least some personnel can be assigned to more than one department or work center, such in the case when employees have been cross-trained on two or more jobs, or for instance, when sales personnel can be transferred between stores. Work assignment from the word itself, it includes work for like employees and management, of course, and where we can apply linear programming to the workforce like scheduling hours. So example problems. McCormick Manufacturing Company produced two products with contribution to profit per unit of $10 and $9 respectively. The labor requirements per unit produced and the total hours of labor available from personnel assigned to each of four departments are shown in Table 4.11. Assuming that the number of hours available in each department is fixed, we can formulate McCormick's problem as a standard product mix linear program with the following decision variables. So let P1 equals units of product 1 and P2 is equals to units of product 2. So we have table 4.11 departmental labor hours per unit and the total hours available for the McCormick Manufacturing Company. So here is, so we have here four columns. The first one is department, then product 1, product 2, and the total hours available. So we will conclude a fourth strain because we will be using department 1, 2, 3, and 4. And we have here the linear programming. Our linear program is maximization of 10P1 plus 9P2 subjected to these four constraints, the 0.65 P1 plus 0.95 P2 less than or equal to 6,500, and the second constraint is 0.45 P1 plus 0.85 P2 less than or equal to 6,000, and the third is 1 P1 plus 0.70 P2 less than or equal to 7,000. And point 7, we'll see the solution for the McCormick Manufacturing Company problem with no workforce transfers permitted. We have here the optimal objective value is equals to 73,589.74359. And we have variable 1. Its value is 5,743.58974 and its reduced cost is 0. And for variable 2, we have its value is 1,794.87179 and its reduced cost is 0. And we have here the four constraint and its slack or surplus and its dual value. For constraint 1, we have its slack's value is 1061.53846 and its dual value is 0. And for constraint 2, its slack or surplus value is 1889.74359 and its dual value is 0. And for constraint 3, its slack or surplus value is equals to 0, but its dual value is 8.46154. And last is the constraint 4. Its slack or surplus value is 0, and its dual value is 10.25641. And in order to solve figure 4.7, we use the Microsoft Excel. We have here the given the department, product 1, product 2, in the hours available, and since our objective is profit or unit, so it's here. It has the production, the schedule, P1, P2, and the max profit. And we'll see the solution in here. Operation Management Application Blending Problems. Blending problems arise whenever a manager must decide how to blend two or more resources to produce one or more products. In this situation, the resources contain one or more essential ingredients that must be blended into final products that will contain specific percentage of each. Blending problems occur frequently in the petroleum industry. Example given is blending crude oil to produce different octaned gasoline, chemical industry, and blending chemicals to produce fertilizer and weed killers. Blending problem example. The Grand Strand Oil Company produces regular and premium gasoline for independent service stations in the southeastern United States. The Grand Strand refinery manufactures the gasoline products by blending three petroleum components. The gasolines are sold at different prices, and the petroleum components have different costs. The firm wants to determine how to mix or blend the three components into the two gasoline products and maximize profits. Data available show that regular gasoline can be sold for $2.90 per gallon and premium gasoline is for $3 per gallon. Product specification for the regular and premium gasolines restrict the amounts of each component that can be used in each gasoline product. Current commitments to distributors required Grand Strand to produce 10,000 gallons of regular gas. So continuation, we have the decision variables as Xij is equals to gallons of component I used in gasoline, G where I is equals to 1 to 2 or to 3 for components 1, 2, or 3, and J is equals to R if regular or J is equals to P if premium. The 6 decision variables are X sub 1R is equals to gallons of component 1 in regular gasoline. X sub 2R is equals to gallons of components 2 in regular gasoline. X sub 3R is equals to gallons of component 3 in regular gasoline. And we have X sub 1P is equals to gallons of component 1 in premium gasolines. X sub 2P is equals to gallons of component 2 in premium gasolines. X 3P is equals to gallons of component 3 in premium gasolines. Total gallons produced of regular gasoline is equals to 5, X sub 1R, 1, X sub 2R, 1, X sub 3R. For premium gasoline is X sub 1P, 1, X sub 2P, 1, X sub 3P. Total petroleum component use is component 1 is equals to X sub 1R, 1 X sub 1P. Component 2 is X sub 2R, 1 X sub 2P. For component 3 is X sub 3R, 1 X sub 3. And for the constraint 8, its lux or surplus value is 3,500 and its dual value is 0. For constraint 9 is 3,500, this lux or surplus value, and its dual value is 0. And for the last constraint 10, its lux or surplus value is 0 and its dual value is negative 0.1000. And that's all of my report. Thank you.